Alright, in this lesson we're going to be learning a way that we can fill holes in graphs or close gaps between two pieces of otherwise continuous graphs. So let's talk first about what it means to be a continuous function. And basically that means that you can trace the function and never pick up your pencil. So if we look at this example, we see that as you trace along from -1 until 3, you're fine without picking up your pencil. But the moment that you hit 3 and after, you have to pick it up to pick up the other piece that's starting up at y equals 4. So this function that's represented would be not continuous at x equals 3. Alright, so if we need to make a function continuous that otherwise would have been if it didn't have that break point, we'd start first by evaluating the function at the break point. And so in the function below, the x value would be x equals 3, where it has the break point. And then once we've evaluated at the break point, we're going to set that equal to the other side of the equation, and we're going to solve for c. So let's try that. So we have a function f of x that's called a piecewise function, and it has two pieces. One is 2x plus c when x is less than or equal to 1, and the other piece is x squared plus 3 when x is greater than 1. Each of these pieces, if they were by themselves, would be continuous. One is linear, continuous on the entire real numbers, and quadratic is the other one. Is also continuous on the entire real number system. So let's read the question here. We're going to find the value of c in here. It's a constant that will make this function a continuous function. So how do we know which piece we're going to evaluate the breakpoint? Well, let's first decide where the breakpoint is. The indicator of the breakpoint would be how the domain is broken apart. You can see that we're in one piece when x is less than or equal to 1, and one piece when x is greater than 1. So that's our breakpoint. So how do we know where to plug one in? Do we plug in the first piece? Do we plug in the second piece? So we are going to evaluate this function at 1 in the first piece, because that is the piece that says when x equals 1. So we plug in the 1 in for x. So I have 2 times x plus c, the first piece, is going to equal, remember the second step was to set it equal to the other piece. When x equals 1 in here, you're going to set it equal there, 1 squared plus 3. Then you simplify and get 2 plus c equals 1 plus 3 is 4. And then you solve for c. So probably the best way to kind of check this, to make sure that it looks continuous, is to graph this now. So I have my function with the c replaced with a 2 to see if it really does match up with those two pieces. And there's a way to enter this in our TIs, and you can enter it in by putting the two pieces in y1 and y2. And as you notice over here, I have used this division bar for a little bit of a different reason than normal. We are dividing the domain when we use that division bar. And we're going to tell it in this piece we are x less than or equal to 1, and in the second piece we're when x is greater than 1. So let me show you where to find those symbols. The parentheses you know, the x I hope you know, the symbol, the less than or equal to and greater than, are going to be the symbols you need to know where to find. And they are under second math. And second math offers all of those symbols there. And so when you enter in y1, you'll go get this less than or equal to. When you enter in y2, you'll get the greater than. So I zoom 6, and I get this graph. And at first glance, I hope you notice we see the linear piece coming up here, and then we see a quadratic piece, but it kind of looks like there might still be a break in there. Unfortunately, that just is, I think, the pixels in this calculator. They're forcing it to look like it's not continuous. Because if I use another program, it matches right up perfectly, as you can see there. So this is a good check to know if you actually did find the right value of C to make it